time to start.
Okay, now I'm officially recording. Um, yes, I think we can start and we'll see. All right. Okay. Can everyone hear me just fine?
Yes.
Yes.
Double checking. Perfect. Thank you. So, good afternoon, everyone. Welcome to our first WTS event for the fall semester 2025. It is our honor to have here with us today Dr. Eleni Christofa. And for those who don't know her, Dr. Christofa is a professor in the Department of Civil and Environmental Engineering at the University of Massachusetts. And she also serves as the Associate Director of the University of Massachusetts. Her research focused on improving the performance, safety, and sustainability of transportation systems. She has made significant contributions in areas such as traffic signal control system, transportation safety, sustainable infrastructure management, with over 1,400 citations. And once again, we would like to thank you, Dr. Christofa, for accepting our invitation. And with that, Dr. Christofa, please feel free to begin your presentation. Thank you.
Yeah, thank you for so much for inviting me. I'm so excited to be here and spending some of this afternoon together to talk to you about my work at the intersection of safety and accessibility. I actually also have a strong, I didn't mention this to Luana or in my bio, but I have a strong connection with the WTS student chapter here at UMass, as I serve as their advisor. So I'm excited to see initiatives like this taking place at other universities and other student chapters. So I want to congratulate the whole team for putting together such a webinar series. And again, thanks for inviting me. So today I will talk to you about the so I guess there's one of the projects is recently completed. And there's another project that we're kind of like midway through. So, I'm not going to be able to present, specific findings from that second one, but give you an idea of the kinds of things my research group has been working on, again, at the intersection of safety and accessibility with a big focus on bike safety. I guess you can see here the video, but I'll show it to you later as well. So why have I decided to spend the last more than 10 years working on bicycle safety? As you're probably all aware, bicyclists are overrepresented in traffic-related crashes. Just in 2022, more than 1,000 pedocyclists lost their lives due to traffic crashes, and about 46,000 were injured. Looking at these numbers, we also need to consider that while they're represented as 2.6% of all traffic fatalities and 1.9% of all traffic injuries, they only account for 0.5% of the commuting individuals, right? So again, they're overrepresented in traffic crashes. And we've seen also an increase in those crashes over the past few years, which is very worrisome. The other issue, which becomes problematic, especially for us researchers, is that a lot of times these bike crashes are underreported. Sometimes, especially if it's not a fatality, people might get up, be able to walk away from the crash. So we don't always end up having data for these types of incidents to be able to analyze them and make recommendations on how we want to design our infrastructure differently, again, to make it safer for everybody. Now, here comes accessibility. So we have been implementing a lot of different designs, one of which is protected bike lanes, as the one you see here on this slide. But by doing that, we have introduced other challenges that we need to be looking at. For example, in situations where you have a bus lane, a protected bike lane adjacent to a bus lane, Then you introduce the challenge, you introduce essentially conflicts between transit users and bicyclists, as transit users would have to cross an active bike lane before getting to the transit stop. So these are topics that we have been working on. How do you integrate multiple modes? How do you design to ensure that everybody is safe and our different types of modes are accessible to everybody? So we'll start with a study that was funded by the Massachusetts Department of Transportation, and it looks specifically at those bus stops I just mentioned that we call floating bus stops. So just to explain a little bit more what these bus stops look like, and my understanding is that Florida does have some of those. I don't know if specifically in your area you have any, but again, you have a protected bike lane. And can you see my cursor, by the way? When I point to stuff, can you
Yes.
see? Okay,
Yeah,
excellent.
I
Thank
see
you.
it. Yes.
So you have a protected bike lane and then a bus stop essentially right adjacent. In some cases, you have a platform where passengers can wait and to board and alight. That platform can be more than 8 feet, in which case we call this full width bus stops. And when it's more than 8 feet, it can accommodate basically a shelter. When it's less than 8 feet, we call them partial width bus stop or floating bus stops. And then there are some cases that there's not even a platform, right? So essentially that forces transit users to wait on the sidewalk and cross the bike lane. Sometimes you find them waiting on the bike lane while they're waiting for the bus, or essentially they have to do that when they're boarding and unloading. And for comparison, you see here to the left a conventional bus stop. In the case that there's no protected bike lane, so essentially the bus encroaches upon the bike lane to be able to load and unload passengers. So what are some advantages of this? Is that obviously we provide a protected space for bicyclists to be able to navigate and go from place to place. And it eliminates this conflict that you saw here that the bus might have with a bicyclist, right? As they're trying to approach the curb space and to be able to load and unload transit users. However, it introduces these conflicts between bicyclists and bus riders that, again, would now have to cross this bike lane to be able to get to the platform, or in the absence of a platform, have to cross the bike lane to board and alight from the bus. And it also creates concerns, particularly for individuals with disabilities, especially the visually impaired transit users and also users of wheelchairs, because they have, for the visually impaired ones, they have to navigate, crossing this active bike lane without having the ability, to see well whether a bicyclist is coming or not. Bicycles are also very quiet compared to motorized traffic. So it makes it very hard for them to be able to cross safely. For those using wheelchairs, it is harder to navigate, narrow spaces on platforms if they're not designed properly. So what we wanted to do in this project is look at how bicyclists and transit riders behave at the bus stops like that, these types of bus stops, and propose some design improvements and guidance on signage and other elements that could make these bus stops safer for everybody and also ensure access for everybody, for all users. So how we went about it, we started by reviewing relevant publications. We looked at various different bus stop design guidelines across the country, but also abroad to the extent that we could, they were published in English and we could review them. And we summarized those. So we saw a lot of variability in terms of how these floating bus stops are named and how they're also designed, what is considered a full width bus stop. So sometimes those dimensions varied from agency to agency. And then we did community outreach by organizing 3 focus groups. We had a total of 21 participants in the summer of 2023. The majority of those participants were from the visually impaired community, and there were a few that were hearing impaired and wheelchair users. And we were able to obtain information about those individuals' experiences. Most of them were from the Boston area, where we ended up collecting the field data as well. So we're able to get the lived experiences of those individuals and understand a little bit better the challenges that they're facing when they're navigating those floating bus stops. In addition to that, we engaged with professional organizations. There was this, I think one of them that answered our questions about how, their experiences and how these are being designed in other places. And we also had interviews with professionals that have been involved in designing floating bus stops, but also cities that have seem to be a bit ahead of the game in terms of how these bus stops are being designed and what elements they're considering. Another aspect of this work is basically creating an inventory of the locations and characteristics of those floating bus stops for the MBTA service area. So MBTA is the Massachusetts Bay Transportation Authority, so essentially the transit agency for the greater Boston area. So we created an inventory with their input on the various floating bus stops and the types of those, along with other characteristics they have. For the behavioral analysis that focused on understanding how transit users and bicyclists behave as they are navigating these floating bus stops, we collected data using LiDAR devices and cameras at 5 bus stops in the greater Boston area. So you see here how they're mapped around Boston and their locations around Boston. The color scheme indicates whether they're a full width platform, a partial width platform, or a no platform floating bus stop. And we collected the total of 36.5 hours of video and LiDAR data collection. Now, the LiDAR data collection allowed us to process trajectories of bicyclists and pedestrians and understand how they interact, but also, extract information about their behavior at these different floating bus stops. And the video could be used for, confirming some of those behaviors and kind of like, observing other behaviors that were of interest. We started with the video data, analyzing the video data. Excuse me. And essentially looking at, as transit users were boarding and alighting from buses, we were trying to extract whether they were looking before crossing the bike lane or not looking. And obviously in some cases we could not tell depending on the angle and where the bus was stopping. So what we found is that for full width platforms, there was a higher likelihood of the transit users looking before crossing. And as you can see from these bar charts, the percentage of transit users that was looking was higher for boarding passengers than for alighting. Often people, when they alight, they just assume that they're immediately on the sidewalk. So I guess that those percentages were lower. Were lower compared to when they were boarding the bus. For the partial width platforms, we observed frequent crosses of the bike path while waiting, which could be attributed to the fact that partial width platforms often have the shelter on the sidewalk. So transit users are expected, or if they want to use the shelter and the bench, they are waiting on the sidewalk side. So therefore, when the bus arrives, they have to cross kind of like fast to make it to the platform and be able to board the bus. So that's why we saw that, there were fewer glances, but also more frequent crossings of the bike path. Other observed behaviors that we were able to extract from videos were things like in this image. So there were at least one of these floating bus stops we collected data at had these longer crosswalks, right? So they were longer in that dimension, very narrow. Obviously, they were just covering the bike lane. But what we observed is that individuals with on those longer crosswalks would just enter it and then walk kind of like diagonally to get to the sidewalk, right? So they extended the amount of time transit users would spend walking within the bike lane, which obviously could be introducing additional conflicts. Now, see here, you see sorry, it's a bit glitchy. You see a video of the trajectories we extracted from the LiDAR device. So the LiDAR, as you can see, was kind of located here. It was able to capture around, capture the movement of different types of vehicles. And through collaboration with one of my colleagues, Dr. I, we were able to extract these trajectories and also classify the trajectories by mode. So you see here we have cars. This I think is most likely a bus, but it was classified as a truck, and pedestrians as well, or two-wheelers and so forth. I wish the video was going a bit more smoothly, but hopefully you get the idea. Oh, it's going on now. Okay. So we used that information to answer a few different types of questions. Some of them were related to the infrastructure and bicycle speed. So how does how we design these floating bus stops affect how fast bicyclists are traveling through those bus stops? We looked at two specific design elements. One was the horizontal curves. So if the bike lane deviates a little bit, like has a deflection as you're entering the floating bus stop area, does it reduce bicyclist speed? And the fencing that you might have seen on some of those floating bus stops, we hypothesized that could also be reducing bicyclist speed, by making bicyclists more aware that there's a bus stop there and there might be people crossing. So we investigated these two design elements in terms of the bicycle speed. Then we looked at passenger behavior. So that had to do with tracking pedestrians and looking at whether they stand in the separated bike lane, how long they spend there, do they go back and forth actually from the sidewalk to the platform and back, and how many of them are using crosswalks versus other parts of the bike lane to cross to the platform or to cross to board and alight when boarding and alighting. And also how many passengers walk across the separated bike path, right? So it's not only about crossing it to get to the platform, but in some cases we observed that individuals were just walking across along the protected bike lane. And lastly, we're interested in understanding the interactions between bicyclists and transit users, or more generally pedestrians. And I'm making this distinction because, as you might imagine, it was not possible for us from the trajectories to understand if a person was necessarily a transit user or not. So we call them pedestrians as a group. So we're interested in seeing when a pedestrian is standing on the bike lane and there's a bicyclist that is approaching, how much clearance do they allow between them and the pedestrian, and do they actually adjust their speeds, especially when there's no platform at those floating bus stops. So we'll present some of the results. As I will discuss, some of them we didn't even have enough sample size to explore. The first one was related to fencing. And so we selected the data from a specific a floating bus stop that had fencing, as you kind of barely maybe see here. So we collected the speeds, the average speeds before the fenced part, and then at the fenced part to be able to compare the two. So as you can see on the schematic to the right, there was some reduction as the bicyclist was passing through the fencing, not through the fencing, by the fencing, along the fencing. But that difference was not that high. However, what we observed was that bicyclists traveling at higher speeds within our sample size, they were more likely to reduce their speed more. So what this tells us is that, okay, maybe overall we don't really reduce the average speed by much, but maybe we bring all the kind of like the highest speeds that we observed lower, therefore hopefully we're improving safety. Then we looked at the percentage of transit riders that use crosswalks versus crossing elsewhere. How we defined the crossing pedestrians was we extracted trajectories that were perpendicular to the bike lane, assuming that's the path they would follow to cross the bike lane. And they were crossing the bike lane at a speed of more than 1.5 miles per hour. What we observed here is that there was a higher percentage of pedestrians using crosswalk at bus stops that had fences. Now, why is that the case? You see an example of that in this middle schematic here that has fencing. It's because those crosswalks are located at the unfenced parts of the floating bus stop. and usually people will not jump over a fence to cross, right? So they were kind of like almost forced due to the design of the specific bus stop to use the crosswalk. So even though we didn't find that fencing significantly reduces bicyclist speeds, it does at least improve safety in many ways by concentrating pedestrians to cross at specific locations of the bike lane that hopefully are more visible to bicyclists due to the pavement marking of the crosswalk at those locations. Lastly, or one of the last results I'll present here, we tried to look at the interactions between bicyclists and pedestrians. So to understand this schematic here, it's essentially at times, it's an XY coordinate system. And you see here kind of like the trajectory of a bicyclist along this green band that represents the bike lane. And then the red dots represent the pedestrian kind of like locations. And what we observed in this specific case is that the pedestrian was actually the one that kind of like slowed down and avoided the bicyclist. And waited for the bicyclist to pass basically before continuing. The issue with this analysis, at least for the specific data we had, is that we didn't have a big enough sample size to be able to do any statistical analysis. So that's left for future work when we can have more information. So out of this whole study, we were able to provide some recommendations. And please note that these recommendations didn't come out of just the behavior analysis that I presented in more detail, but it had input from the focus groups we did, the professional organization outreach, the interviews we did with cities, the guidelines we reviewed, both the US-based ones, but also the international ones. So we put all this together. And essentially, we had recommendations under kind of like 3 sections. So first one was to maximize separation between bicyclists and pedestrians. How you do that? By designing your platforms to be at least 8 feet. So the so-called full width floating bus stops. And that will also enable you to have enough space to be able to locate shelters and benches on the platform. If in the cases that this is not possible to be done due to space constraints, what can be done is you can convert a parcel width or full width platform by narrowing the bike lane at the location of the bus stop, or moving the shelter from the sidewalk to the platform. So even though you keep the platform narrower, which again could create issues for individuals that are using wheelchairs and how they're able to navigate them if they're narrow, but at least you can move the shelter there to allow people to wait at the platform rather than rushing when the bus stops to cross the bike lane. Installing fencing, again, can encourage individuals to use the crosswalks. And very important is to use different pavement materials to make clear and improve situational awareness for all the users that of that bus stop or of the area around the bus stop, that they're able to detect and differentiate between where the sidewalk is, where the crosswalk is, where the bike lane is, and so forth. In general, and this was a big part of the focus group discussion, was that no platform bus stops should be avoided. And some other things we discovered from other cities around the world is that there is actually laws kind of like dictating that bicyclists should not be passing and should be yielding to transit users when they're passing through one of those bus stops. So you see here a bicyclist stopped in Copenhagen as the board is alighting as the bus is alighting some passengers. You see pavement markings in Toronto indicating that you're not allowed to, to pass when the bus is actively boarding and alighting passengers. And then in Taipei, in Taiwan, you see that buses have this bus stop sign similar to what our school buses in the States have, indicating that you're not allowed to be passing a bus that is, again, actively boarding and alighting passengers. Another element we had recommendations for is speed management for bicyclists that can be achieved by other horizontal deflection. So changing essentially the curvature of the bike lane, hoping that will cause bicyclists to reduce their speeds, or vertical deflection, so a slight elevation that would allow bicyclists, that again would motivate bicyclists to slow down. In Cambridge, they have already, in other places around the country, they have already been also implementing some pavement markings, like the one you see to the right of the slide, which says yield to pedestrians. And it remains to be seen what impact these types of markings could have on, again, encouraging bicyclists to slow down and be more aware that there might be some active crossings of the bike lane, especially when buses are present. Last but not least, I mentioned at the beginning, we're very interested in this, and we worked actually with the Department of Accessibility of MBTA to understand what challenges these floating bus stops introduce for individuals with disabilities, especially the ones with visual impairments. So recommendations that have come out of the study were to align the crosswalk, tactile pavement, and boarding area in a straight line. So it basically eliminates much of the need for navigating more complex situations and design. So transit users can just walk straight and get to the place where they will be boarding the bus. Marking the locations of the crosswalks by installing, a flex post that's indicative of a bus stop being there. So it's easier for individuals with visual impairments to be able to detect that. And in general, again, trying to make the navigation from the curb to the bus as smooth as possible and as easily detectable as possible. So you see here some examples. There's different, in certain places, they install different types of tactile pavement exactly where the bus is stopping, as an indication that that's exactly where you need to be waiting to be, to board the bus. And they have also secondary bus ID poles that is in Braille, so people can actually read that with their hands. So this is the team that worked on that. It was a collaborative research effort with Northeastern University and Dr. Firth's research group. I mentioned it was funded by Mass DOT. We work closely with MBTA System-Wide Accessibility Department, and we're also grateful for the Massachusetts Commission for the Blind support, who helped us recruit participants for our focus groups. And of course, the support of our transportation center. So currently, where we stand with this study, my PhD student, Thomas, that you see here on this slide, is continuing this work by collecting additional data to be able to study specifically the fencing and horizontal curvature aspects that we were not able to, result in conclusive outcomes in a couple of different cities, so we're able to also see if there's any differences from place to place. The second part of my talk relates to more directly bicycle safety, but again, seen through the lens of how interactions with other modes affect that safety and how the infrastructure we design for bicyclists and for all users in multimodal transportation systems can improve bicyclist safety. So I guess this is, I can't remember if I have it later, so I'll let you watch a couple of seconds of this. So this is one of the videos we collected with drones about a year ago now. And we're working on extracting the trajectories this is the project I will be talking about next. So far, so as I mentioned at the beginning, I've been working in this space for more than 10 years now. And so far, the tools we have used to be able to assess safety, especially bicyclist safety as it pertains to the design of our infrastructure system, has been done through mostly driving simulator experiments. We're using eye tracking to observe where drivers are looking at and see if they're able to detect bicyclists or detect the bicycle infrastructure we have in place. Recently, we have also been working on building a bike simulator. So we're really close to having it actually up and running. And that would allow us to not only observe the driver behavior as it pertains to their interactions with bicyclists, but also bicyclist behavior when we introduce them to different types of design elements. And last but not least, a lot of my work is out in the field, which is great because that's where you get the actual real world behavior. So we've been doing data collections for many years with radar devices, video cameras, but also more recently LiDAR devices. So this is actually the first project I got involved in that was directly related to bicycle safety. It was a driving simulator study evaluating different types of bicycle infrastructure treatments. So you see here a Shero, basically a conventional bike lane, but it's like a bike through lane because it kind of like continues and it allows for a right turning movement to be moved to the right-hand side of the bike lane. A bike box in a conventional bike lane, right? So we're able to see how drivers behave around these treatments. Granted, some of these treatments, like the bike box, at that point, almost 10 years ago now, were not very common in Massachusetts, right? So we also were interested in seeing, can drivers that are not familiar with these types of infrastructure treatments, can they actually understand what they mean and behave as expected? We moved on with this work by adding, so these were a mix of like intersection treatments and link segment level treatments. So by adding combinations of those treatments, so we looked at what if we have bicyclists what's the driver behavior like if we have bicyclists coming from a conventional bike lane into a protected intersection or into a non-protected intersection versus a protected bike lane coming into a protected intersection or unprotected. This was motivated by the fact that some research has shown that, when we have protected bike lanes, the bicyclists are kind of like removed away from the travel lanes. And therefore, when we arrive at an intersection, drivers are less aware of the presence or potential presence of bicyclists. And therefore, they're less likely to kind of like scan the environment to be able to detect them. So we're interested in seeing if kind of like the combination of intersection and segment treatments has an impact on driver behavior. We have expanded some of this work now to look also at comparison of driver behaviors when they're interacting with bicyclists versus e-scooters, again, in the presence of some of these treatments. Two of the studies I performed in the field that were funded by the Massachusetts Department of Transportation were related to understanding driver behavior and bicyclist behavior around bike boxes, which are these rectangular, spaces that bicyclists are expected to wait as they're waiting for the green light to go through the intersection or perform any other maneuver at the intersection. And the two-stage turn boxes that facilitate left-turning movements by separating the left-turning movement of a bicyclist in two stages, as the name implies. So a bicyclist would go through and then wait at this two-stage turn box and then complete their left-turning maneuver once the green light for this through direction is on. So the summary of findings from this work has been that the effectiveness of these treatments is highly influenced by drivers' experience, both as a bicyclist, but also their understanding and their familiarity with these treatments. In protected bike lanes, we actually found also in our study that they could be contributing to lower situational awareness. And the presence of bicyclists induced safer driver behavior. So there were more glances, there were slower speeds, and this speaks to, the so-called safety in numbers phenomenon, right? The more bicyclists out there, the more likely are for drivers to be aware that there might be bicyclists and driving more safely. So this is an example of like a design intervention that you could make for a protected bike lane to reintroduce it back with the general traffic as you're approaching an intersection. So you see this bike lane is not only curved, so it has a horizontal deflection, but also it's painted green. That's hopefully more visible to drivers to, again, be more aware that bicyclists might be around. Lastly, when we looked at intersection level treatments, we found that protected intersections were successful in achieving higher number of glances and lower speeds. That's because at protected intersections, drivers have to slow down and complete the right turning maneuver at a lower speed and further away, right? So it's at a wider angle that they complete this turn. Therefore, they're also more likely to interact with a bicyclist kind of like in front of them rather than having to scan to the right or towards the back diagonally. So that makes these types of intersections safer. Now, when we looked at the bike boxes, we found that there was lower motorist compliance compared to previous studies. What we mean by that is when you approach a bike box as a driver, you are expected to stop behind basically the perimeter of that bike box. So what we saw is that about 75% of their participants were actually doing that. And that's a higher compliance that we observed in the simulator study compared to the real world, that was 60%. And the other thing we observed was that turning vehicles, had statistically lower compliance rates compared to through moving vehicles. And the reason being, as you can imagine, as you're completing a right turn, you probably want to be kind of like further ahead at the intersection, within the intersection, to be able to have better visibility. Lastly, most bicyclists, when we look at bicyclist behavior at bike boxes, they utilize the bike box part that was right in front of the bike lane. So they didn't really move to be in front of the bike box, in front of the vehicles, which could potentially improve their visibility even more. And left-turning vehicles were left-turning bicyclists were more likely to use the region of the bike box in front of the travel lanes, especially if they were taking advantage of a protected left-turning maneuver. For the two-stage turn-queue boxes, we saw a very low utilization from the bicyclists. We found no correlation between the intersection size and the bike lane presence on how many people are actually using two-stage turn-queue boxes. We found that when we didn't have dedicated left turns or dedicated or protected left turn phases, we saw higher utilization because probably that's when bicyclists feel more unsafe just making a permissive left turning maneuver at the intersection. So they elect to use the bike box, the two-stage turn-queue box. And we also saw higher crosswalk use from left-turning bicyclists when there was not a two-stage turn-queue box that was present. Oh, I forgot I had these animations, apologies. So as to indicate that, like, again, at the bike box, most bicyclists waited at the area B or even C within the bike lane, and very few that wanted to turn left utilized the A space. And here is an example of a bicyclist using the two-stage turn-queue box properly, right? So they came from here, stopped here, and waiting for the green light to move through. So the objectives of this study are that we did with the drones is to collect data from a group of drones that are flying at the same time over a long stretch of an arterial segment, and use these trajectories to develop surrogate safety measures for bicyclists and correlate the risk we observe, the crash risk we observe, with the presence of the different bicycle infrastructure treatments, but also the connectivity of those. So we selected a 0.35 mile segment of Beacon Street in Somerville, Massachusetts. This is basically a city very close to Boston and to the west, I guess, of Boston. We flew 5 drones. You see here the overlap of the drone imagery. The idea was that when we have overlap, we can actually trace the trajectories of both bicyclists and cars and kind of like observe them over longer parts of this signalized arterial. And we were there for 4 days with 7 pilots, 5 drones, and we were able to collect a total of 18 hours of video data from across along that whole arterial segment. Now, the reason we selected this specific this specific signalized arterial was that it presented a lot of different bike infrastructure treatments that would allow us to then assess their impact on bicycle, but also on car safety. So we had conventional bike lanes on this part. We had a buffered bike lane that's essentially a conventional bike lane, but with those bollards, right? So it has some level of separation, but it's not fully separated. We had protected or separated bike lanes. We had bike boxes. There were other places that we had two-stage 10Q boxes. So you see here an example of a bike box at one of the intersections leading to the bike box from a conventional bike lane. Further down, there was a buffered bike lane. So again, we're able to assess behavior also as these treatments change along the segment and also at the intersections. Again, for this middle drone, we had conventional bike lanes and protected bike lanes, and a two-stage 10Q box, another design treatment that we're interested in studying. And you see here how a conventional bike lane transitions to a protected one. There is a two-stage 10Q box here, so this is an image from the actual intersection, a bike box and a conventional bike lane again. And lastly, the last segment had just conventional bike lanes, which is great because we can use it almost as control for the rest of the study as we assess the impact of the other types of treatments on bicycle behavior and driver behavior, bicyclist behavior and driver behavior. So here is a schematic of the trajectories we're able to extract. So we actually, I would be remiss if I didn't mention that we collaborated with a startup company in Switzerland called Mobilisis to be able to, who were able to process the video data and extract the trajectories for us, and were the process analyzing trajectories, developing surrogate safety measures to be able to assess, again, crash risk and other safety challenges that appear, and be able to present some recommendations about how these different designs should be implemented in the real world. The estimation of surrogate safety measures, we're targeting time to collision and post-encroachment time. Just, as a review for those of you that are not familiar with these terms, time to collision is essentially the time that it would take for a following vehicle to crash into the preceding vehicle if they do not change their trajectory at all or their speed. And post-encroachment time has to do with the time that elapses from the moment the vehicle is leaving the conflict area until the next vehicle is approaching that area. So obviously, the shorter these times, the higher the risk, right? And that's how we can assess crash risk. A lot of times, particularly important for bicycle safety, that, as I mentioned at the beginning of my presentation, we have underreporting of bicycle crashes. And obviously, we don't want to wait to see a bike crash to be able to, go and analyze and see what might have been wrong. This is from the bike box study we had done. So you see here kind of like an example of a bicyclist in a car, and that's to show you that, by plotting trajectories like this, you can actually analyze how, close these two modes were and assess the risk. All right, so the safety assessment, we have a few dependent variables that are obviously the two surrogate safety measures, motorist speed, but also bicyclist speed. And for independent variables, we'll use the type of infrastructure treatment, the connectivity of the bike lane network, the intersection level treatment density, but also bicyclist and car demand, and as well as the roadway geometry to be able to understand how each one of those factors might be influencing these dependent variables. This was funded by the New England UTC, again, in collaboration with Mobilisis and UMass Air, who helped us recruit pilots. You see them here that were flying the drones for many days. There were many early mornings that we spent in Somerville last fall, and we're excited to analyze the trajectories and see where that goes. And the lead student on this project is my PhD student, Thomas. So that concludes my presentation. Hopefully I'm within time, and I'm happy to answer any questions or discuss any topic that you might found interested related to this work. Thanks again.
Thank you, Dr. Christofa, for the presentation. It was really good, and thank you for sharing your time with us. And yes, I would like to open the floor for any questions. If you guys want to unmute yourself and ask, or just type in the chat box and I'll read it out loud.
Hey, Dr. Christofa, thank you so much for your presentation. I have one question, maybe more general question about bicycle safety. So, okay, in Florida, we don't have many cyclists because I think of the weather and the general culture. But based on my experience in cities like Seattle or Washington, I noticed that some cyclists, maybe these are the ones who are quite reckless and they don't actually pay attention to the pedestrians. So, do you feel like the more familiar they become with driving, riding their bicycles in an urban scenario, the more reckless they tend to become?
That's a good question. It's hard to answer that question, without actually analyzing the data. The truth is that if we, in a truly multimodal system, right, or in the complete streets design world, right, you should be designing a system that is safe for everybody, right? So that takes in the system, safe systems approach, if you have heard of that term. The idea is that you design with so many kind of like countermeasures and expecting that humans are going to make mistakes, are going to be reckless, whether they're the bicyclist or the driver, right? So even when those things happen, people are still safe, and at least you don't get to see fatalities. So again, that's, I mean, I'll tell you what I saw, like staying there along this arterial for like hours at a time for multiple days last fall, that the types of bicyclists that were traveling through this area was all kinds of bicyclists you can imagine. There were parents that had like a kid in the back and a kid in the front, right, in those bicycle seats, or on cargo bikes. There were the kind of like fast, like more athletic ones, right? So you could see that there's all kinds of people that, because of the infrastructure the city has selected to put in this on this arterial, feel safe to be able to ride. And the other thing I want to say is relates to the safety in numbers, is that the more bicyclists are out there, the more they're going to feel safe, the more they're going to be visible, the more used cars will be to them. And I'll also share a personal kind of like observation from me as a driver. And I have been a bicyclist in my life at different times in my life, but not currently. But growing up in Greece, and you might know that, Ioanni, is because we have so many motorcycles. As a driver, I was always aware that there might be a motorcycle coming from right or left, right? So I find myself kind of like having the same scanning patterns here, even though even here where I live in Amherst, there's not that many bicyclists, but I feel like I'm a bit more aware of the potential of someone being, right, than I would be if I had not learned to drive in such an environment. So I think it's all a matter of exposure and obviously education. We can try to, I mean, it was one of the recommendations that came out of this study, is like just make sure that people understand what these treatments are like and how they need to behave around. But yeah, I mean, we cannot control. I guess I'll end with that because I feel like I diverge from the question you initially asked, that I don't think we can ever like fully control human behavior, no matter what mode user is coming from. But we can at least design our systems to have some like safeguards that even if humans don't behave exactly how we would like them to, then we still don't see traffic fatalities.
Okay, thank you. So the only thing I wanted to add is that, to be honest, when I was in Seattle and I wanted to use those crosswalks, I didn't feel actually safe because I noticed those cyclists, they were not aware of my presence there. That was my concern. And I was like, because there are many bicycles, they feel safer and they have their attention only on vehicles, and then they forget to check about pedestrians. That's like the feedback I have. But yet that was only for like a weekend. Didn't spend
You mean
more
about the
time.
floating bus stop, the protected bike lanes that lead to bus stop?
No, I'm talking about the crosswalk. Like yes,
Or
you
like
have
a
to.
regular, like the one here on the image?
Yeah, probably like
Yeah.
this one.
Yeah. So you
So
would say the bicyclists were going too fast?
yes, they did. I thought they should have to yield to the pedestrians.
Yeah, so I mean that's where we can see, how to address this with like proper signage or pavement markings and see if those make a difference. And sometimes campaigns also help, or like laws, things that go into law, right? Like they have in other countries that like you have to stop when you're crossing along a bus stop and so forth. Yeah.
Okay, thank you so much.
Hi, Professor. I have a quick question.
Yes.
Do you think having protected bike lane have any impact on the attention of driver? If it is yes, how? Why might protected bike lane sometimes reduce, attention of driver?
Yeah, so you're talking about protected bike lanes, did I understand
Yes,
correctly?
yes, yes.
Yeah, so the protected bike lanes, I mean, typically are further away, right? Sometimes they're even separated by a parking lane.
Mhm.
Therefore, you might not even be seeing the bicyclists, right? You might be paying attention to the cars that are parked along the travel lane. Bicyclists are further removed, so therefore you're less aware of their presence or their potential presence. You don't necessarily see the green paint or whatever color it is in different places. It varies. So that contributes to lower situational awareness, which again could have an impact on the safety as you're approaching at the intersections. Now, protected bike lanes are designed in all kinds of ways, right? In some cases, as I said, you have the parking lane. In some cases, it's just like elevated, like on the sidewalk. So it depends also on the distance you have. But that's a topic that we are still kind of like trying to to research and understand what the actual impact is on the situational awareness, and again, what can you do at the intersection to be able to mitigate any impact it might have on how aware they are.
Thank you. Do you have any specific result after applying this kind of, methodology? What is the result for reducing the accident number? I mean, what was the exactly impact on the safety?
Yeah, so the studies in the driving simulator, obviously, even if a crash happens as a participant is driving the simulator, that you don't count it as a crash, and they're very rare. And it doesn't look like a crash, anyways. So the way we're assessing it in the simulator is by like our performance measure is whether the speed was reduced, whether their glances increased, or the driver looked at where they're supposed to be looking. So we found that they do contribute positively to those kind of like safer behaviors. Now, out in the field, on the bike box side, we assessed it based on how, because we didn't have trajectories of cars for that one. We assessed it on whether they are waiting behind the stop line of the bike box or not, and we saw that about 60% does that. We didn't have before data, so we're not able to compare that. For these treatments, this is the first study I'm doing in the field for like the segment level treatments, right? And the combination of the treatments at the intersection of the segment. This is the first study I've done. So I will need to come back to a future seminar to be able to tell you our findings. Because we're, as I mentioned, we're still analyzing those trajectories we collected to be able to develop those surrogate safety measures and see what we find. Yeah.
Thank you for an interesting topic. I think it's really useful for Florida, especially around of the campus, because we have a lot of bicycle that typically they don't use, car. And maybe this idea, I mean, at least for Florida, maybe it's interesting topic. And thank you for interesting presentation.
Yeah, thanks again.
Yeah, I was thinking about the bike situation, as Rahila said, around campus is where we see more, because sometimes people commute on their bikes to campus. But unfortunately, we don't see much here in Florida. I mean, my dad and my brother, they do like to bike around, but at least near my neighborhood, we don't have any like bike lane at all. So it just got really dangerous.
Mm-hmm.
But this is, yeah, I think they should think about, I guess some people don't even consider biking to places here in Florida because it might be dangerous, like driving really fast. But I do notice on myself, like I reduced my speed for sure if there's someone biking around. I think that would be a good idea
Yeah.
if they were to implement more biking lanes here.
Yeah, I mean, hopefully this is helpful, even if, and I don't know, maybe all of you have been to other places as well, but to kind of like get the first idea of like what these treatments look like or what the research around them and their impact on safety has been to date. And yeah, so Florida, I actually have not visited your university in that area, but other places I've been, if it's anything similar, the roadways are very wide, right? I mean, it's obvious that they have been designed for motorized traffic. So, and the distances are big, right? Like there's a lot, like cities are spread out. So, those things are not conducive to, bicycling as a mode for like everyday commutes and meeting other needs. But we can change that, right? I mean, we can redesign as long as the good thing is that there's space there, so you can redesign it and reallocate it if you want to make an environment that is more conducive and safer for everybody.
Yes. Unfortunately, I know a few people who have lost other people like close to them due to accidents on a bike here in Florida. You know, it's very unfortunate, but hopefully that can be changed with time.
Yeah.
Yes. Well, I think there will be no more questions.
We don't have any question.
Okay.
Okay, Christofa,
Yes.
I have a question regarding
Oh.
the drone video processing. If I understand correctly, it's not easy to accurately identify the bicyclist and identify the speed from the drone video compared to vehicles. So I'm just wondering how you improve the algorithm or what algorithm you use to make sure the speed is accurately extracted from the video.
Yeah, so that's actually, are you talking about the bus stop study or the drone study?
The second one, because you use drone video for the bike.
Yeah, so that one actually we did not process the trajectory. We're going to analyze the trajectories now that we have them, but we did not process the video to extract the trajectories. We worked with Mobilisis to do that, and my understanding is they're using AI algorithms to detect, mode, classify their mode, and then obviously, track their trajectory. So I'm happy, if you have an interest in that, I'm happy to connect you with them, but it's not something I was involved in, or I think they would necessarily be shared. But
okay. I just know that this has always been challenging, so it's not easy. But yeah, if they did a great job, I would like to hear what kind of algorithm they used.
Yeah. Okay.
Okay. Thank you.
Thank you.
That was a nice question.
Thank you, everybody, for coming.
Any other questions from anyone? I think that was it. I think we're doing questions. I don't want to get anyone here. All right. Thank you so much, Dr. Christofa.
Yes, thank
This
you
was
again for
very
inviting
interesting
me.
presentation. Yes, and it's great to connect with you and WTS. It's nice.
Yeah,
Hopefully
yeah.
we can connect with your chapter too.
Yes, that would be great. Maybe we can plan like a joint webinar at some point. I know it's going to be hard for everybody to travel, right? But that could be, maybe we can talk about doing something like this, for the spring semester and, doing it together. This is a great idea. So I want to congratulate you for doing this work and bringing other speakers
Yes.
from across the country to the group of students.
Yes, no, that would be great because I'm actually starting to think about the spring events for a chapter. And I'll definitely check you guys on the social medias.
I
Are
don't
you
think
guys
we have.
active on any social media
Yes, I can
that I
email
can
you.
contact them?
It's a joint group because we kind of like have joined forces with the IT chapter we have. So I can share with you.
Nice.
It's called JTO at UMass, but I can share with you their handle. So we can keep in touch through that too, and you can see what activities we're into. And yeah,
Yes, that would be great. Thank you.
excellent. Thanks
All
again.
right. Thank you once again for your presentation, and thank you everyone for attending, for your questions. This is great. Thank you. Have a good day.
Bye.
Thank you.